In this section, 18.4, we're going to be learning about how to calculate the spontaneity of redox reactions. How spontaneous are these reactions? And the word spontaneity probably, hopefully, makes you remember or think about Chem 162 when you first were introduced to the concept of spontaneous and non-spontaneous reactions. So this is going to use some of the stuff that we learned in that chapter, Gibbs free energy. So I want to very quickly remind you of spontaneous versus non-spontaneous. So as an initial reminder, spontaneous, that is a word that we use to describe a process that can happen all on its own without us needing to provide any sort of extra input. And a non-spontaneous process is one that won't happen on its own. We have to do something to make that reaction go, like maybe give it some heat. And then we have a third category, equilibrium. Equilibrium is not spontaneous and it's not spontaneous. It is a simultaneous back and forth reaction, forward and backward, moving at the exact same rate. And in addition to our definition of spontaneous, meaning it's a reaction that happens all on its own, we also learned that the technical definition of spontaneous was that when we calculated the delta G for a particular process, it was a negative number, negative delta G. And a non-spontaneous process, when we calculated its Gibbs free energy, we would get a positive value of delta G. And when we were in equilibrium, if we calculated delta G, we would get 0. For a reaction that's in equilibrium, delta G is 0. So we also have some values of E cell that correspond to spontaneous and non-spontaneous. So we haven't talked about this yet, but you can probably make some guesses. It's going to be logical to make some guesses about the value of E cell at these different conditions. So for a spontaneous reaction happening the way that it's supposed to happen all on its own, electrons, if we're thinking about redox, electrons moving spontaneously from one side of the cell to the other. In that situation, we said E cell is always going to be positive. When the cell is left to do what it wants to do, move the electrons in the spontaneous direction, the value of E cell is always going to be positive. And so you can imagine that if the electrons are going in the wrong direction, the value of E cell would be a negative number. And also, if we had a redox reaction that was in equilibrium, we would just end up with an E cell of 0. So very similar and logical signs for these different reactions. So the relationship between delta G and these E cells can be given to us with a mathematical equation. The amount of energy in terms of like kilojoules or joules, the amount of energy that can be produced by a redox reaction can be calculated or given by this equation, delta G, so this is the amount of energy, and if we're dealing with standard conditions, we'll call it delta G standard, is equal to the, I'm going to kind of write this in a weird order here. I'm going to go from right to left. The cell voltage, E cell, so how much energy is that cell giving off, times a constant, which we call Faraday's constant, and which is our conversion factor between joules and volts, and also times the number of electrons that are being exchanged, the moles of electrons that are being exchanged as the electrons move from one side to the other. Because as you can imagine, if you have a lot of electrons over on one side and you've got a lot of electrons that can move to the other side, you're going to get quite a bit of energy out of this. And last but not least, there needs to be a negative sign in front of the equation. Why does there need to be a negative sign? Well, because of the incompatibility between the sign of spontaneous delta G and spontaneous E cell. When E cell is spontaneous, it's going to give us a positive number. And so for us to be consistent, we've got to throw this negative sign in there to kind of just switch that up. So this is the equation that we will use if we want to calculate the kilojoules of energy that's produced by a voltaic cell. So let's define all the variables in this equation. Delta G is our Gibbs free energy, and this is what we're using to relate to spontaneity. Not just its sign, but also the magnitude of the number. And then E cell, as you know, is the cell voltage. And it's calculated by taking the voltage of the cathode minus the voltage of the anode. So we've already learned that. F is a constant. As I said, this is a new constant, and this is called Faraday's constant. And as I said, this is the conversion factor between joules and volts. And its value is 96,500. That's a comma, not a decimal point. 96,500. Units are joules per volt times mole of electrons. So that's kind of a weird unit. This is, and again, this is the amount of energy per volt per mole of electron that's being exchanged in a redox reaction. And then last but not least, we have lowercase n, which is the moles of electrons that are exchanged. And in order to get this number, the moles of electrons that are exchanged, you have to look at the total overall balanced equation. You can't just look at a half reaction individually, because remember, sometimes when we combine our half reactions together, we have to change the stoichiometric coefficients to get them to combine. So you've got to look at the whole entire balanced equation to get your n.